Okay. So yeah, so we have this as our final answer. So this would be in increasing stability, which is the same as increasing basicity, because the more, oh, well, my bad, decreasing stability, excuse me, decreasing stability, okay, the more stable a base is, the weaker it is. Okay, so yeah, that's how you would do this problem. Alright, so that's done. Alright, so moving on to the next problem is this one. So I have a molecule here, a giant molecule with some circle hydrogens, and I want you to rank the circle hydrogens in their increasing acidity. So you'll encounter these two different types of, I guess, acid-base ranking problems. You'll be asked to rank problems. Like in problems, you'll be asked to rank like different molecules, or just rank hydrogens within one giant molecules. And you apply ARIO the same way, whether if it's, among different molecules or just within the same molecule. Okay, so let's just keep ARIO in mind and apply it to the different hydrogens within the same molecule. All right, so again, to use ARIO, you need to make sure that your hydrogens are pulled off and that you're looking at the conjugate base, okay? Yes, I know this is gonna be a pain, but for me, I have pre-drawn all of the hydrogens pull off in their separate molecules. I hope you guys did this as well. I know it's gonna take a lot of time, but this is what you should do, okay? So yeah, so actually let me go ahead and start numbering the hydrogens so that it'll be a little bit easier for me to point to. Okay, we have 7 hydrogens again. They're a circle. Alright, so let's look at, I guess the first one I have here is the 6th hydrogen. Okay, so this is number 6. Okay, so let me go backwards a little bit and go back to ARIO. Right. We are applying ARIO, so we should stop at atom effect first. So once you pull off the hydrogen, okay, the negative charge will be on different atoms, okay, within this molecule, okay. The atoms are going to be a sulfur atom, some oxygen atoms, and carbon atoms, okay. So we have sulfur, oxygen, and carbon. And just like how we did with the selenium, nitrogen, and carbon, okay, atom effect states that because sulfur is bigger than oxygen, it is better at holding that negative charge. So sulfur would be more stable as a base than oxygen. Because it is more stable, it is more acidic. Okay? See how that that terminology is. There may be some confusion here and there, but the more stable the base is, the more acidic its conjugate acid is, okay? So I asked you guys to rank them in increasing acidity. So oxygen, like the hydrogen on the oxygen, would be less acidic than the hydrogen on the sulfur, okay? And then oxygen, the hydrogen on the oxygen atom will be more acidic than the carbon hydrogen, okay? So now we can have some sort of a preliminary ranking, okay? So we have up here 1 as our only sulfur, so it will be the champion in being the most acidic hydrogen. Then we have the oxygen atoms. We have 2, 3, and 5. So 2, 3, and 5. Don't know how to differentiate them yet with the atom effect. So now we only have 4, 6, and 7. 4, 6, and 7. Alright, so now we can move down the list again. So we just apply atom effect to reach our preliminary ranking. So now atom effect gets us nowhere now, so we use the resonance. We would look at the resonance effect now. Okay, so we don't need to apply the resonance for sulfur because it's already the one single most acidic hydrogen there is, okay, in this molecule. So we can look at oxygen, the hydrogen on the oxygen next, okay? So okay, then I would show you these molecules that I've pre-drawn. Okay, so we have the oxygen here, and then the oxygen here with their hydrogens being pulled off so that I'm looking at the conjugate base. Okay, make sure you have the conjugate base there to apply ARIO, or else things are gonna get a little bit muddy. Alright, so resonance. Which one or ones of these will be able to partake in some sort of a resonance stabilization? These two, right? So this one will not be able to resonate its negative charge away, okay? We have 2 hydrogens here already, so cannot break octet. Alright, so this will be less acidic. So now we can refine our ranking again. Which one is this? This one is 5, so 5 would be right here. Okay, well, let me just put down the carbons as we're not really looking at them right now. Okay. Alright, so next, let's look at these two. So let's look at these two, okay? So this one right here is kind of like, it has the similar path for its resonance as this molecule that we just looked at, okay? Can resonate up and around the ring and nowhere else, right? Just around this ring, okay? So there are some resonance stabilization right there. In fact, there are 3 resonance structures, 3 more resonance structures that it can produce. But this one has only 1 resonance structure. It can just resonate to another oxygen atom. Now here's another caveat for the resonance effect. Okay, if you are able to resonate the negative charge between two of the same electronegative atom, that adds even more stabilization to the base, okay? So I'm trying to say this one resonance structures, they're resonating between two oxygen atoms, two electronegative oxygen atoms, is way more stable than this one oxygen atom resonating between, I guess, three carbon atoms, okay? Now, this totally agrees with the pKa trend. This functional group right here, this OH group bonded to an aromatic ring is called a phenol, and it has a pKa of 10, around 10. And this is your good old carboxylic acid group. And a carboxylic acid group has a pKa of around 4. Lower the pKa, the more acidic the hydrogen is, okay? Because the conjugate base of this acid is way more stable, okay? So this is more acidic, okay? This is more acidic. So now we can refine our ranking even more, okay? So that will be 3, and that will be 2, and 1 is still okay. Yeah, keep drawing commas when it's supposed to be that symbol. Okay, 1 is just, first one. Alright, so now let's apply the same thing to the carbon atoms, okay? 4, 6, and 7. Right. So I have 4, 6, and 7 here. So this is 7 right here. This is number 4 here, and this is 6 right here. Okay, so this one does not have resonance, so it is the least, it is